problems on the test? Number three? Yeah. The overall, the scores were good. So this is exam 2, number 3. It's the one with the beam positioned vertically. There's a 300 Newton force like that. It has a mass of 100 kilograms, so just to not clutter it up, I'm going to write it like that. But what this means is that that downward force is acting at the center. 981. There's a pin joint at the top. So that's a full force vector. Then at the bottom, there's a pin and slot joint. And so you have a force with a known direction, call that RB. And so you just represent that with one scalar variable. And you can put your origin and about point wherever you want. I'm going to put both of them at A, at the top. So for that force vector RA, there's no row vector. And so there's no moment. This thing has a length of 2 meters. So these two forces that are acting right at the center are at the coordinates 0, -1. So the row vector is 0, -1. The force vector, you can do them as two separate ones or combine them. If you combine them, you get -300, -981. And then the moment is -300. And then the last force is at the bottom. That's 0, -2. The about point's the origin. So the row vector is 0, -2. And that force vector is at an angle, let's see, so I think a good way to think about that is if there's your coordinate system, that slot makes an angle of 50 degrees with the x-axis, and then you have to go another 90 degrees to get to the direction that I drew. This is 90. And so this RB is acting at an angle of 50 plus 90, so 140. So theta is equal to 140. And so that's -0.766 RB, positive 0.643 RB. And so you get whatever 2 times this is, -1.532 RB. How did I get it? So on the coordinate system, I drew a vector that was pointing along the slot. And we know that the force is perpendicular to the slot, so it's 50 degrees to get from the x-axis to here, and then another 90 to get here. So 50 plus 90 is 140. Or I could have gone 50 to get there, minus 90 to get there if I'd drawn my arrow the other way. Or I could have drawn my first vector like this, and that would have been more complicated, but there's a few ways you can do it. And then from here, you just write out the equations and solve the algebra. Any other questions about the test?
Number 1.
Number 1 is the Pulley one. So for these, you always isolate all the hanging stuff. So that's 1 pulley in the mass. The weight of this is 80 times 9.81, so 784.8. And then coming out of what you've isolated are 2 cables. Well, it's the same cable, so they both have the same magnitude, but it's coming out at one point here and at one point here. So we'll call those both T since it's the same cable. And the angle representing this one is 80 degrees. The angle representing this one is 100 degrees. They're each 10 degrees off of vertical. So Newton's second law says well, this one is 80 degrees from the positive x-axis. This one's 80 degrees from the negative x-axis, which you could think of as 180 minus 80, so it's 100. And then the weight's 0, negative 784.8. And then you're solving for T. So that's for, and if you solve it, you get T is equal to about 398. So that's the answer for part A. For part B, it's asking the force that the cable applies to the ceiling. So that's like, what's this force vector? Where this angle is 80 degrees. And so that force vector that's applied to the ceiling by the cable is equal to 398 times cosine of negative 80 degrees, sine of negative 80 degrees. And then for the third one, the force you're looking for is the force the cable's applying to the wall. Where this angle's 30 degrees. And so the force on the wall by the cable is equal to 398 times the cosine of 150 sine of 150 By the way, what if I had asked what's the force vector that that pulley that's attached to the ceiling has to be in a fixed joint with the ceiling. What if I'd asked what are the loads applied to the ceiling by the, what do you want to call that, by the post for that pulley. Anyone have an idea how to do that? Mm-hmm. Yeah, so let's just isolate that whole, let's isolate the pulley and the post that it's attached to. We're assuming this is weightless. So we have one force like this. We have one force like this, and we know what both of those are. And then this makes a fixed joint with the ceiling, so that means there's an unknown force of R, and then a couple MR. And I guess if I had given this distance, this length, we could use Newton's second law and rotational Newton's second law to calculate R and F, R and M, I mean. Any questions about that one? Any other questions about other parts of the test?
I guess just the angle for the roller on number 2.
Yeah.
Can you just set up that problem?
Yeah, sure. So number 2, it has a mass of 20 kilograms, so there's a weight of 196.2. There's a horizontal force of 500. There's a pin joint at the bottom, so I'll call that RA. And then there's a roller at the top, and that's perpendicular to the surface, so we know the direction of that. To come up with that angle, I guess you could think of, okay, so there is the, there's a vector that is directed along the surface, and we know that this angle is 60 degrees. So to go counterclockwise from the positive x-axis to this vector is 120. And then we know our vector is perpendicular to that. This is the one that we want. This is the direction of that force RB. So we have positive 120 minus 90 gives us an angle here of 30 degrees. So that force produced by RB, I'll call it the vector FB, is equal to RB times cosine of 30 sine of 30. If I put the origin down here, the point A is 0, 0. The point B is, what's the length? 1 meter? 1 times cosine of 150 sine of 150 which is negative 0.866, positive 0.5. And then the point C, the midpoint, is the average of these two. So you can think of that as 0, 0, plus negative 0.866, positive 0.5, divided by 2. And so that's negative 0.433, positive 0.25. So now you have all your coordinates. You can represent all your forces as vectors, and you're ready to go. Okay. Number 4, really the only mistake people made consistently was that 400 Newton meter couple was in the clockwise direction, so you had to make it negative. Okay, so that's the test. So now back to centroids. Centroids are the geometric center of an object. Anybody remember without looking? What did I say are the 2 types of problems that we're going to use this for? Yep, that's right. To find the center of mass of an object and to do distributed load calculations. The center of mass of an object is important in a lot of ways in mechanics. In statics, the only thing that it's important for is figuring out where to apply the weight force. In dynamics, it's more important because F equals ma says that the acceleration you care about is the acceleration of the center of mass. But so for statics, it's just the weight that we're dealing with. And I went through a calculation that says for a right triangle, a general right triangle, with a base B and a height h, we calculated that the center of mass is here. Where this distance is base over 3, and this distance is height over 3. And we did that using the complicated integral formula. So I want to show a calculation of how you use this. So say that you want to figure out the centroid for a right triangular shape where this is a right angle, this distance is 2, this distance is 5, and let's say that the origin is at the top. Okay, well, we know that the centroid is here. How do we know that? I guess the way you can think of using this triangle formula is for each one of these two dimensions, along each of the two legs, one side of that leg is intersects like a wall, and the other side runs into a point. Okay? That's how a triangle works. Maybe you've never noticed that before, but I bet you have. So we're going 1/3 of the way from the wall toward the point. Okay? No matter what direction it's oriented. That means that this distance from the wall towards the point is that full distance over 3, and this distance is 1/3 of that length, so 2/3. Okay, so we know those distances, but now we have to translate those into coordinates, and so you have to be able to kind of. It just takes a little geometric, physical thinking about directions. So okay, if we know this distance is 2/3. Finding the x-coordinate is pretty easy because it's 2/3 in the positive x direction from the y-axis. So this is just going to be 2/3 x. But it takes a little more thinking to figure out what the y-coordinate is going to be. So the way I'm going to do that is think of this, if you're all the way down at the base, that would have a y-coordinate of -5, but we're not going quite that far. We're 5/3 short of 5. So this is going to be -5 plus 5/3. And so that's -10/3. Any questions about that? So using these formulas, that's really what it's going to be about, just turning these shapes around in your head, going from distances that you know to translating that into coordinates. I'm going to give you a few other formulas for a few other shapes. Before I do that, I'm going to tell you two useful... Oh, no, I'm not. I'm going to give you the shapes first. And there's a list of these shapes on D2L. I'm not going to tell you all the ones on there. I'm just going to tell you the ones we're going to use in our problems. So the first one is a right triangle. And for all of these, I'm going to give you the X centroid, let me do it like this. Okay, so if this is the centroid location, I'm going to call this distance y centroid, this distance x centroid, and I'm going to give you the area too. So the x centroid distance is b over 3. That distance y bar is h over 3. And the area is b h over 2. Next, I'm going to do a semicircle. The radius is r. Call that lowercase r. The centroid is here. We'll call this distance y bar. The x location of the centroid is nothing. It's right on the center line. The y location of the centroid is 4r over 3 pi. And the area, well, you know the area of a circle is pi r squared, so this has to be pi r squared over 2. Next is a quarter circle. Again, the radius is r. That distance we'll call x bar. This distance we'll call y bar. Then x bar is 4r over 3 pi. Y bar is 4r over 3 pi. And the area of the quarter circle is pi r squared over 4. The next one is a parabolic shape. The centroid is right on the center line. So there's no x bar. And that y bar is 3h over 5, where this distance is h. And the area of that shape is, let's see, also define this length A, that's 1/2 of the width. Then the area is 4AH over 3. And then the last one is 1/2 a parabola. Semi-parabola. So again, let's say that the height is h. And A means the same thing it did before. then we'll call this distance x bar, and this distance y bar. So x bar then is equal to 3a over 8. Y bar is equal to 3h over 5, the same as it was for the full parabola. And the area is half what it was before, so this is 2AH over 3. There are two shapes missing from this list that seem sort of obvious that, you know, we would definitely want to know. Why are we skipping a rectangular shape and a circular shape? And the reason that those aren't in this list is because of the next thing. One key fact for finding centroids and that is if you can find a line of symmetry in the shape, the centroid has to lie on that line of symmetry. We saw that in a couple of these shapes that this held. There are two shapes in this list that have lines of symmetry. The semicircle has a line of symmetry up the middle, and the centroid lies on that line of symmetry. And then the parabola, same thing. There's a line of symmetry, vertical line of symmetry, and the centroid lies on it. What this means is that any shape that has where you can find two lines of symmetry, the centroid is defined. It has to lie where those two lines of symmetry intersect. So if you can find two lines of symmetry, the centroid lies at the intersection. So what that means is that for a rectangular shape, or a circular shape, the rectangle has a line of symmetry there, a line of symmetry there, and so we know all we need to know about the centroid. It just is right at the middle. The circular shape has a line of symmetry there, a line of symmetry there. You can find infinitely many of them, but any two you choose intersect at the same point, and so that has to be the centroid. The same idea works in 3D. We're not going to do 3D centroids, but the same idea works in 3D. The difference is in 3D we're talking about planes of symmetry. So the centroid must lie on any plane of symmetry two planes that intersect at a line, so that's not enough anymore to specify the location of the centroid. But if you can find three planes of symmetry, those intersect at a point, and that point defines the centroid. So if you can find three planes of symmetry, the centroid is at the intersection. Okay, so now using these formulas for more complicated shapes. I've given you a list of 4 or something shapes, 6 or so if you include the rectangle and the circle. But that's obviously, like, most of the things you're going to want to deal with are not any of those shapes. So how do you use these simple shapes to come up with the centroid of complicated shapes? So I'll call that building up complicated shapes from this list of simple shapes. The way you do that is there's a sum formula that you can use for centroids, and it looks very similar. It's sort of like a finite version of the integral formula. So you can think of it as the centroid of the whole body is equal to 1 over the total area times the sum over all the simple shapes. Let's say there's n simple shapes, so the sum from 1 to n of the area of each simple shape times the centroid of each simple shape. And it also works for subtracting one shape from another one. Bless you. So x, y can be equal to, okay, well, let me draw a picture here. So say you have this shape, and you want to remove this shape. So call the whole thing A, and the inner thing A1. Then the centroid of just, you see what I'm getting at here. So you have this sort of funny donut shaped thing. You want to find the centroid of that. You can do that as 1 over A minus A1 times the quantity A times the centroid of the outer shape minus A1 times the centroid of 1. Bless you. The same idea works in 3D. So since we're not going to use this, I'm putting it in parentheses again. But the centroid of a complicated shape is equal to 1 over the total volume times the sum of the over all the pieces of the centroids of the pieces. Oh, and I forgot something here. This should be the sum over all the pieces of the volume of the piece times the centroid of the piece. Dot, dot, dot. The subtraction thing works too. So, for example, if you want to find the center of mass of a person, you could approximate their body with a bunch of rectangles. You can make it as complicated as you want. Break it up into this, 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 this. That's not a rectangle, that's a triangle, I suppose. You know what I mean. Break it up like that. Call this body 1, 2, 3, 4. Go through all those pieces. Find the centroid of each of these individual things and the area of each of these individual pieces, and then use that sum formula to come up with the center of mass of the whole thing, the centroid of the whole thing. Any questions about that? Okay, let me do an example. So let's say we have a T shape. Where this distance is 0.2 meters. This is 0.1 meters. This is 0.05 meters. And this is 0.2 meters. And let's put our coordinate system here, right on the center line. Bless you. And we want to know what the centroid is. Well, we already, without doing any calculations, know one thing about the centroid. We already know one of the two components. Can anyone tell me what that is? Yeah, it's got to be on that y-axis because that's a line of symmetry of this shape. And so the only thing we have to figure out then is the y component of the centroid. We know that x bar is equal to 0 from symmetry. So let's break this up into these two rectangles. I'll call that 1 and that 2. And I'm going to figure out the location of the centroid, the coordinates of the centroid of each of these, and figure out the area of each one of these. So rectangle 1. What's the, I guess we only have to do the y components. That's what I said up here. So let's just do that. So what's the y centroid coordinate of rectangle 1? So it's up 0.2 to get to the bottom of the rectangle, and then another 0.05 to get to the center. So that's 0.25. And the area of that rectangle is 0.2 times 0.1, so 0.02. And then rectangle 2. What's the location of the y centroid for rectangle 2? Yep, positive 0.1. And the area of that is 0.2 times 0.05, so 0.01. And so the total formula says the y centroid is equal to 1 over the total area, which is 0.03, times 0.02 times 0.25 plus 0.01 times 0.1 and you get the sort of boring result 0.2. Well, we just calculated 0.2. So that's the height of the y centroid. It just happens to be right on the point where rectangle 1 and rectangle 2 meet. So the centroid locations are 0.2. Any questions about that one? Why? Because of symmetry. Any line of symmetry you can find for a shape, the centroid has to lie on it. So this, you can imagine folding this along the green line. The two sides would match up. So the centroid has to lie along the green line.
What are you multiplying in the parentheses? 0.02 and 0.2?
I'm multiplying the area of the individual shape times the centroid of the individual shape. Any other questions?
So you can't add up all the areas and add up all the centroids and multiply those.
Nope, it's different. Doesn't work like that. Okay, well, let's take a break, but let's do this one when we come back. So let's say we have a rectangle where this is 2, this is 1, and then we remove a circle from it. So the circle is completely inscribed in this half. So the circle is removed from the rectangle. What's the centroid? And I suppose let's choose a coordinate system like this. Okay, so start again at 206. Yep. Yeah. Sure. Okay.
So I had, yeah, like T here.
So,
Pretty sure there should always be T.
so let's calculate the centroid of this shape. So I'll say shape 1 is the full rectangle. And shape 2 is the circle. So for shape 1, the area is 2 times 1. What's the centroid of the rectangle in this coordinate system? Yep, it's 1 over the middle of the rectangle, and 0.5 up is the middle of the rectangle. Everybody see that? And then for shape 2, the area is, so the radius of this circle is 0.5. So the area of the circle is pi r squared, which is 0.25 pi, or pi over 4. And what's the centroid of the circle? You go 1 over from the origin to get to the left edge, and then another 0.5. So that's 1.5, and then for y, it's 0.5 again. And in fact, if we think about symmetry, we know that this is a line of symmetry, so we already know the y location of the centroid. We could just calculate the x location. A total is 2 minus pi over 4. And so now we can use that sum formula. The total centroid is equal to 1 over the quantity 2 minus pi over 4 times the area of the rectangle times its centroid minus the area of the circle times its centroid could someone calculate that and let me know when you have an answer? I guess you can skip the y components if you want. We know that's going to come out to be 0.5. Zero 0.68, and this is 0.5. So the centroid is somewhere over here. Okay. And so now the way you would use this in, so now imagine that shape let's use it in a rigid body statics problem. So let's say we have that shape. And it's connected to a pin joint up here. And a roller at the bottom. And let's say the total mass is equal to 100 kilograms. What are the reactions? Well, free body diagram. We have a force vector up here at the pin. Call that RA. We have, I'll call that N, the normal force from the roller. And then we have a weight force acting down, and it's acting at the center of mass of the body. And that, that's equal to the mass of the object, so 981. So now I'll fill out the table. Pancake, artist, row, 4, marzipan. Well, I'm going to use the old coordinate system. This one. But I'm going to choose A as the about point, just because I can. So the point A, the coordinates are, what was that? 0, 1. The about point is 0, 1. So this force vector RA doesn't have any row vector. The forces are X and Y components, and the moment's 0. Now I'll do the weight force. That was the one we just calculated, the location we just calculated when we did the centroid. So that's at the location 0.68, 0.5. The about point 0, 1. So the row vector is 0.68, negative 0.5. The force vector is 0, negative 981. And so what's 0.68 times negative 981? 667.08. And then the last one is that normal force. That's at the location 1, 0. About point is 0, 1. So the row vector is 1, negative 1. Force vector is 0, n. The moment is n. So Newton's second law says RAX, RAY plus 0, negative 981 plus 0n is equal to 0. the moment equation says negative 667.08 plus n is equal to 0, so n is equal to positive 667.08. And so RA is equal to 0x, and then what's 981 minus 667.08? 313.92 newtons. And you can see that that 0.68 came into the calculation in the moment produced by the weight. So changing the shape to move that centroid around, like say you moved around where this missing circle was, it would affect the reaction forces. Any questions about that? Okay.
So in your free body diagram, include anything about the effect of having the circle out? Is it just easy by shifting the forces around?
Yeah, I don't think there's any reason to, I mean, I wouldn't object to drawing that gap in the free body diagram, but that's probably more detail than is really helpful in a free body diagram. I just tried to draw a fairly accurate location for where the weight force is. That sort of has the same effect. Okay, so that's how you one more thing about that. Notice that when you're using the centroid to figure out where the weight force is applied, you never care about the y position of the centroid. It never matters in the problem, and that's because you can always move the weight force along its line of action, which is up and down. So you could always calculate the horizontal centroid and just leave the y centroid as 0 for the calculations. Okay, so that's how to deal with the weight of, so far in this class we've only dealt with rectangular objects and circular objects, but now if you have other shapes, that's how to figure out where the weight force is applied. So now let's talk about distributed loads. Yep. Like in Spanish? I can't. The thing about the y position not mattering? Yeah, well, I think drawing it is probably the best way. So if you have an object like this and the centroid is here, the weight force acts there. But remember, with the equipolant forces thing, you can always move any force vector along its line of action without changing the problem. This is the centroid, but you could treat it like the centroid was anywhere along this line of action without changing the behavior of the problem, because, well, you can move forces.
Perpendicular distance, which is that the whole thing is perpendicular. I understand that, but where are you calculating it from? That's what I'm trying to figure out.
Like, what's the about point?
Yeah, what point are you using?
As the about point?
Yeah, as your zero coordinate. So yes,
Where's the origin?
It doesn't matter. Like, it would be the same story no matter where. Let's say that the origin is here and the about point is here.
but as long as it's not the same, so that can't be you can't use your center of mass as your origin.
You can. Here, I guess, here's all I'm trying to say. So look at look at the table here, we said that the weight force was applied at what we calculated to be the centroid, 0.68, negative 0.5, right? The location where that force is applied, it comes up in calculating the moment produced by that force. And notice that that negative 0.5, because of the direction of the force, that never comes up in the cross product. So we could have made that a million or negative 5 or 0, and we would have gotten the same moment. And so that's why this 0.5, the vertical position of the centroid, didn't matter in the calculations.
So that's the same concept you're talking about before. Then I
Okay. When I do try to talk in Spanish, I have to like explain my way around everything because I only know like 7 words. So I'd have like centroid would be like the place between the left and the right, you know? Okay, so distributed loads. Or like I was trying to say the song Freebird to my friend in Spanish recently, and all I could come up with was Parrot of Liberty. Okay, distributed loads. So you see these. So here's like a rigid body problem. We've done a lot like this. So you have a fixed joint with the wall. Say it's 2 meters long, but the loads that we've dealt with so far have been like point forces. You know, maybe there's a point force acting at the end or something. But you can also have these forces spread out over some finite length or area. And the way that appears in problems is like this. They'll draw a shape and say that at any given location, the height of this distributed load tells you at that location the number of newtons per meter that are being applied. So let's say this is over here at the right end, this is 10,000 newtons per meter. And the way to think about this is so distributed load versus force vector. Think about this kind of as an analogy with instantaneous velocity versus distance traveled. So first, if you have a distributed load like this acting on this shape, what's the total force applied, say, at this point here? The answer is there's no finite force applied at a single point. Just like in a single instant, your car doesn't travel a finite distance at a given speed. You have to integrate it over some amount of time in order to get a finite distance. And it's the same with this. A distributed load only produces a finite force over some finite interval. Okay, so let's say so a distributed load only produces a finite force over an interval of distance, or let's say an interval of x. It's the same thing as if you're talking about a car moving with an instantaneous velocity or speed. It only travels a finite distance over an interval of time. And then second, well, this is pretty related. At a single location, a distributed load applies an infinitesimal force. Just like at a single instant, the car travels an infinitesimal distance. Okay, so what we're going to do with distributed loads is we're going to figure out how to come up with an equipolant system where that distributed load is treated as a point force, because we know how to deal with point forces. So for calculations, we want to find an equipolant system where the distributed load is replaced by a point force. So the way to do that is think of the distributed load as a shape. So for example, the one that I just did above, that shape is a right triangle, and this isn't drawn to scale, but you can still do the calculation. The height on this side is 10,000 newtons per meter. The base is 2 meters. Then the total point force is the area of the shape. And second, that point force is applied at the centroid of the shape. Okay, so let's do this example. So we have a fixed joint with a wall, a 2 meter long cantilever beam, a triangular distributed load, and we want to know what are the reactions at the wall. Well, we have to figure out, in order to replace this distributed load with a point force, we have to calculate the area of that shape to figure out the total point force, and we have to find the centroid of that shape to figure out the location where we can apply it. So if this is 10,000 and this is 2, the area is equal to base times height over 2, so 10,000. And what are the units of the area there? It's Newton, so all the units are going to come out just right on this. And then the centroid is equal to we're going to use the formula for a right triangle. I guess let's put we have to choose a coordinate system. Let's put it here. So it's going to be 1/3 of the way along the 2 meters. So that's going to be -2/3. And it's going to be up 1/3 of the way along the 10,000, so that's going to be positive 10,000 thirds. And this is in meters. So what I did was just calculate I just calculated the location of that centroid using the formula for a right triangle. Since this force is directed straight down, just like the weight, it doesn't matter where we put the vertical component of the centroid. So this 10,000 thirds doesn't end up mattering at all. But the -2/3 is going to matter. So I'm going to draw a free body diagram now of the beam. So we have a downward force of 10,000 newtons. Acting at a distance of 2/3 from the wall. And then at the wall, this is a fixed joint, so we have a force vector, call that R, and a reaction moment, MR. And I'll write out the table. Okay, the origin is at the wall, so R acts at the origin. I'll make that the about point too. So the row vector is 0. Force vector is Rx, Ry. Moment is 0. Then there's that reaction couple. We don't care about any of this stuff, so that's Mr. And then there's this point force we just calculated. This one won't matter, so I'm not even going to put it in there. if you want to put it in, it's fine. It won't mess anything up. So the location is, where that point force is applied, is negative 2/3. And I'm just going to put the y component as 0 because it doesn't matter. So the row vector is negative 2/3, 0. The force vector is 0, negative 10,000. And so the moment produced by that 10,000 Newton force is 6,666.7. And now the two equations, you have Rx, Ry, plus 0, negative 10,000 is equal to 0. And the moment equation, you have Mr plus 6,666.7 is equal to 0. So the reaction force at the wall is 0, positive 10,000. And the reaction couple at the wall is equal to negative 6,666.7 Newton meters. And the value of that reaction couple would have changed depending on where this point force acted horizontally. Any questions about that? Let's do one more. Okay, I'm going to do a cantilever one again because that's the calculations are the easiest, and we can just focus on the centroid, on the distributed load. So let's say that we have a cantilever beam. Maybe let's put the wall over here this time. And let's say we have a distributed load that's rectangular, where this is 5,000 newtons per meter. And let's say that this is 0.5 meters, and this is 0.5 meters. And let's say also that the mass is equal to 50 kilograms. What are the reactions? Okay, well, first let's figure out what's going on with this distributed load. Let's put the origin over here. The height of this rectangular shape is 5,000. The width is 0.5. So the total point force, the area of that shape, is 0.5 times 5,000. And what's the centroid location? Remember, we only care about the X centroid. So yeah, it's 0.5 and then half of the way along, so this is at 0.75 meters. So free body diagram. We have the weight acting at the middle of the beam. How big did I say that was? 50. So that's 490.5. And then here we have a force of 2,500. And then at the fixed joint we have a reaction force and a reaction couple. And you can fill out the whole table for this, and if you're comfortable with that, keep doing it. We're going to do a lot of these horizontal beams for the next couple topics, and you'll get pretty good at doing these without filling out the table. So Newton's second law says Rx, Ry plus 0, negative 490.5, plus 0, negative 2,500 is equal to zeros. So the reaction force is 0, 2990.5. And now for the moment equation. We'll make the about point at the left end point. Okay, so what's the moment, if the about point is at the left end point, what's the moment produced by this R? It's 0 because that force is acting at the about point. That couple, you always just add on. It doesn't matter what the about point is. That's a pure moment. Then you have the 490.5 acting with a moment arm of 0.5. So we have the moment arm, we have the 490.5. Now all we have to think about is, would that cause a positive or negative rotation around the about point? It's clockwise, so it's negative. And we'll do the same thing with this one. What's the moment arm, the distance from the about point to the 2,500 force? Yeah, 0.75. The force is 2,500. Would that produce a positive or negative moment? Negative again. All this is equal to 0. So MR is equal to 245.25 plus 3/4. What is it? 1875. Thank you. 1875. And so what do you get when you add those together? It's impossible. Okay, so this is newtons. This one's Newton meters. Any questions about that? But that's the first time I've done it in this class by thinking about the moment arm and then multiplying by the force and then the direction. It works if your moment arms are going to be are perpendicular to your forces. It's easy to do then. But you could just as easily fill out the whole table and do these calculations and you get the exact same thing. As we go on, we'll get used to this sort of quick way of thinking about simpler problems like this. Okay, done.